think you can start, Annika.
Yes, I just did a mistake here when I was going to share, but I think that is also good so that people have a chance to arrive. I still see that we're not in steady state when it comes to the number of people. But yes, let me just see if I can get everything in order here on my screen. And then I would like to say welcome to everybody. And now oops, sorry, now it's gotten wrong here again. I'm sorry about this. I don't know why it doesn't want to share the right one.
I think it was the right one. Yeah.
So, do you see my screen now?
Yeah.
Okay,
I see your
excellent.
screen. Everything okay.
Excellent. Then let's get started. Welcome everybody to this webinar with the title Aerosols from Sea Ice Sources, Does the Climate Care? My name is Annika Ekman and I am working at Stockholm University and also within the project CRiceS, who is behind this webinar. So before we dive into the topic, I will just give a very brief introduction. So first of all, for those of you who are not members of CRiceS, CRiceS stands for Climate Relevant Interactions and Feedbacks, the key role of sea ice and snow in the polar and global climate system. And you see the three main objectives of CRiceS here. And well, the overall aim is basically to improve our understanding of the coupled climate system in the polar region. So looking at the interactions between different compartments of the climate system. To obtain new knowledge about polar and global climate, and thereby also enhance our ability to respond to climate change. And there are four core themes within CRiceS, and one of them is aerosols and clouds. So why are we interested in aerosols and what is an aerosol? For those of you who are not working with that every day, an aerosol is a solid or liquid particle suspended in the air. And on average, as a global average, aerosols cool climate. So if we look at the observed current warming, and that is about 1 degree at the moment compared to pre-industrial times. And then if we use numerical models to look at what governs this warming, then the main part is, of course, driven by anthropogenic emissions of greenhouse gases. That is what really causes the warming. But at the same time, we have anthropogenic aerosols that mask some of the warming. So we have both a warming component and a cooling component that together then results in the bit more than 1 degrees warming that we have currently. So anthropogenic aerosols, they come from different sources. So industrial, agriculture, forest fires, and so on. And this is what then really governs the cooling. But the background is also important. So what we have in terms of natural emissions of aerosols also impacts the magnitude and the uncertainty of the cooling due to anthropogenic aerosol particles. And as you can see here, this uncertainty is currently very large. So that brings us into today's topic, which is aerosols from sea ice sources. Does the climate care? And we will have two presentations to start with, one by Marcus Frey from the British Antarctic Survey in the UK, and one from Rémi Lapère from IGE and Latmos in France. After that, we will have a panel discussion, and there we will also include Ruth Price from BAS and Ulas Im from Aarhus University. And at the end, we will have some final remarks. Please feel free to ask questions in the chat during the talks if you want something clarified. We will also open up the floor to questions through the microphone at the end of this webinar, hopefully. But also remember to turn off your microphone and your camera while that one is turned off, actually. So the microphone while other people are speaking, so that we don't have any unnecessary sound. Okay, then I will leave the word to Marcus Frey from BAS. He has been a researcher there since 2008, and he is focused on physical and chemical air-snow exchange processes, especially sea salt aerosols lately and their interaction with clouds.
Okay, thank you for the kind introduction, Annika. Can you see the screen? Not in presenter mode yet. Okay.
Yeah, looks good.
Perfect. Yeah, so welcome everyone. Aerosol from sea ice during Arctic winter. Observations and climate impacts is the title of my talk. So coming really from an observational point of view. First, I would like to acknowledge here a large number of people, the bus team, the wider Mosaic team. Most of the observations I'm going to talk about are coming from the Mosaic International Arctic Drift Expedition from 4 years ago, which helped to collect samples and run instruments, huge effort. And that effort started also already before CRiceS. But CRiceS helped us a lot in interpreting and modeling the data and get actually that coupled understanding of a coupled system. I'll describe a little bit the context and then focus on the climate impacts of fine sea salt aerosol from a new aerosol source above sea ice, looking at the Mosaic data and describe a first climate sensitivity test using a model. And this is based on two CRiceS publication. One is the Gong et al. From 2023, you're probably also already familiar with, and one which is nearly accepted in the Mosaic special issue in the journal Elementa. So just as a reminder, Arctic amplification is a phenomenon described for the Arctic that we see the Arctic is warming 4 times faster than the rest of the globe. On the left, you see like the observed temperature trend for the last 4 decades, and the red hotspots are indeed in the central Arctic. However, our global climate models, they have a low bias overall too cold and don't capture that increased warming in the higher latitudes. This is due to incomplete understanding of processes, mainly feedbacks. One of them we know, sea ice albedo feedbacks. You take away a white sea ice surface and you have a positive feedback loop having accelerated warming. But there are others, less well understood. One reduced to reduced air pollution, which actually leads to a cooling, or Arctic haze, which leads to increased cloud formation and surface warming. Due to the poor understanding of these processes, however, the models are still not doing a good job, as we see. Polar aerosol, yes, there are local and remote sources. So you have, of course, as the main contributor to the background aerosol sea salt from the open ocean, but then also from the mid-latitudes, Northern Europe, North America, and Russia, mineral dust and black carbon reaching the Arctic and contributing to the mix of aerosol observed there. Transport is supposed to be happening only in winter and spring, whereas in the summer, the polar dome limits the meridional transport and local sources dominate. Until recently, sea ice covered regions of the ocean have been considered as basically source free because it was thought that the sea ice act as a lid and cover. However, evidence shows now that there are actually sources related to sea ice. For instance, frost flowers, highly saline ice crystals, which grow into the air and which may get mobilized, open leads, so these open water in the fractured pack ice, or blowing snow, which I'm going to talk about a little bit more in detail later, sublimating snow particles which contain salt and other impurities released to the atmosphere. All this aerosol has a climate impact by influencing the atmospheric radiative transfer. One, through the aerosol direct effect, that is through scattering and absorption, both in the UV visible and thermal infrared. And then also, and that's this aerosol indirect effect, through the impact on clouds, cloud seeding. So there's particles called CCNs, cloud condensation nuclei, which form liquid water droplets. That's mostly inorganic salt, black carbon, and then others called INPs or ice nucleating particles, which actually nucleate ice crystals leading to ice cloud formation. And these are mostly mineral dust or marine organics. Clouds are poorly understood in the high latitudes and not well presented in the models, but have a huge impact on the surface energy balance, as they, for instance, trap thermal infrared emitted by the Earth's surface and radiate it back to the surface, so leading to surface warming. Looking a little bit closer detail to the sea ice surface, in winter, spring, it's mostly polar night, but you have like a range of surface types going from the open ocean, where you have sea spray aerosol formation going through the marginal sea ice zone, frost flowers, and then open leads and the fractured pack ice, and then snow-covered sea ice, where you have, in fact, salty snow going into the air and potentially releasing impurities. We focus here on sea salt, but there's other chemistry in the ocean, for instance, DMS, dimethyl sulfate, product from phytoplankton, which undergoing oxidation forms also particles which have an impact on clouds, just on the side. We focus on blowing snow, so snow crystals picking up salinity from the surface of the sea ice or from sea salt deposited through atmospheric deposition, lofted into the air, undergoing sublimation, and then releasing the small aerosol particles, which can be reaching levels where clouds form or even get transported further away, for instance, to the Greenland ice sheet, where we measure these particles then in ice cores. We know from the Antarctic observations that the sea salt must be related to sea ice. That's one is that models had never really reproduced observed wintertime maxima in sea salt, because the advection from the open ocean was too weak. So it had to be a source closer to the continent where the ice core was drilled. And a chemical fingerprint, which worked in the Antarctic, which pointed to the sea ice as a source of this aerosol. Sea ice sources are, of course, open leads and frost flowers, although recent evidence from the lab suggests that it's less likely that these particles, that they play a role, and blowing snow. What's the climate impact? Well, we don't know. We had to do more measurements. To go a little bit back in time also, the blowing snow mechanism was a model hypothesis until recently, until we found first evidence in the Antarctic. And just to say, it's more, the parameterization in the model is a little bit more complicated than the classic parameterizations of sea spray, for instance, which depends on wind speed and temperature. Here, for the blowing snow, important model parameters are also snow particle size and snow salinity, and then of course temperature, wind speed, relative humidity, and to a third stage order also like snow age, describing a little bit the sintering of snow and the reduced mobility as snow ages. So these have to be input into the model to get an estimate of the mass flux of sea salt aerosol from that mechanism. An interesting detail of this model understanding, or this idea, is also that you can calculate the dry diameter of a sodium chloride particle, knowing the original snow particle diameter and the salinity. And the contour plot shows you like the dry particle diameter in this plot here, and the blue box, the range of the parameters observed in nature. To the right of the dashed line, supermicron, and below actually a large range of like submicron particles, which can be produced by this mechanism. And here on the right hand, a size distribution of observed sea salt aerosol during blowing snow, and in red, the model prediction. So the model predicts, as here, a lot of fine aerosol, but to date, there were no observations to actually validate this prediction. So we had to do more measurements, and we had MOSAIC as a great opportunity to access the Central Arctic in winter and spring. So it's the 1 year drifting expedition from 4 years ago, where we deployed instruments on board of the ship, but also in situ, right on the sea ice, which allowed us to measure aerosol concentrations and properties in fine temporal and detail. Go right into the coarse aerosol observations. Here an example from the first half of December in 2019. Panel A shows you the wind speed as soon as it crosses a drift threshold. You have in black symbols in black symbols, you have then in panel B immediately lofting snow particles. So they're fairly large particles, 50 to 500 micron during these two events. And in panel C, then in the size range of 0.5 to 20 micron, coarse aerosol also increases, one weaker and one stronger. During those periods, also the relative humidity above ice is below 100%, inducing sublimation. Going back to the top panel, how do we know that actually sea salt plays a role in these observed particles? The blue symbols is actually the sea salt fraction of aerosol below 1 micron, based on measurements using an aerosol mass spec. Then again, just as a broad observation over the entire winter-spring period, so from November 2019 to May 2020, snow particle number concentrations increase, of course, with wind speed, and coarse aerosol shows also an increase, although the relation is noisier. If you do some statistics and compare blowing snow in red here and non-blowing snow time periods, the size distribution, you see a systematic increase across all sizes between 0.5 and 20 micron. And also looking at monthly averages on the right-hand side, except April, always an increase if you take a monthly average. Then we moved on to improve the existing model. So currently, we see here as well the increase in snow particle number density with wind speed, but also the particle diameter on the right-hand side increases with wind speed. However, in the model, there's a fixed snow particle size distribution. So we replace that with one which depends on wind speed, which is highly variable. And the model is then the red line here, which mimics quite well the observed particle diameter of the snow particles. And I jump over this here, and putting this all together, implementing the mechanism for blowing snow into a global chemistry transport model, P-Tomcat, we the calculations suggest that there's a significant increase of sea salt aerosol in polar winter, both hemispheres. Moving on now to the fine aerosol, and this is more in detail now the Gong et al. Paper. Again, here, a closer look at 3 events from November and December 2019. Strong winds above the threshold, depicted here in the red line. Relative humidity above ice dropping below 100%, and snow particles observed in the air. We look now at the fine aerosol, so that's total number concentration in the range between 10 and 300 nanometers. Fine aerosol, here the black line, show increases above the background during the blowing snow events. What are some of the characteristics of these particles? Here, observations from a CCN counter, so the concentration of cloud condensation nuclei at 5 different supersaturation ratios. So always also an increase, quite significant over these 3 events. Looking also at the size distributions, so the one outside the snow, not as non-blowing snow period in black is low, whereas the ones from the 3 events significantly above. And then looking at statistics over the entire winter spring during mosaic, always blowing snow conditions show higher coarse and fine aerosol on average, and also the CCN at all supersaturation ratios are elevated. The challenge is, of course, always like what are these particles made of? The aerosol mass spec has some uncertainties in the sea salt estimate. Another strong lead that the observed particles are actually sea salt aerosol is by looking at the particle hygroscopicity, so the kappa value. So you see on the left plot, the blue and cyan symbols and error bars are kappa values during blowing snow, and then in gray and black outside of the blowing snow periods. And during blowing snow, they are above 0.7, ranging to 1, so much closer to the lab-determined hygroscopicity of sodium chloride. Whereas outside the blowing snow period, it seems that hygroscopicities dominate, which are more similar to organics or ammonium sulfate. So that's a good lead that this is actually sea salt aerosol, which is being observed. Taking the observations now into the model. So the model here is a different one. It's the global chemistry transport model, GeoSChem. Thomas is run with and without the blowing snow mechanism. And on the left-hand side, you see a prediction for the entire Arctic north of 70 degrees north. And this computation suggests that the blowing snow produced sea salt particles accounting for almost a third of the total winter aerosol concentration. So quite significant, in implying also a 10-fold increase of cloud condensation nuclei from that source. Taking now these CCNs and cloud droplet numbers calculated with the model and observed cloud liquid water path, the clouds are simulated. In fact, the cloud long wave downwelling emissivity and averaging over the Arctic, a warming is calculated of about 2 watts per square meter during cloudy days between November and April. So quite significant in order of magnitude here. I summarize now what you have here. Sublimating blowing snow produces sea salt aerosol in Arctic winter and spring. So we have found the first evidence that this is happening also in the Arctic. We can see that blowing snow mechanism as a recycling mechanism, injecting aerosol back into the atmosphere. Aerosol, for instance, which had been deposited previously to the snow, is remobilized. And fine sea salt aerosol from blowing snow can act as a cloud condensation nuclei and potentially leads to significant surface warming via clouds. And this process has not been included so far in the models. However, the uncertainties remain and challenges. This is again from the observation point of view. It's always a challenge to distinguish between locally produced particles, aerosol, and distant sources. So local sources include also open leads, which will play a larger role in a warming Arctic, of course, and the distant sources, long-range transport. Size distribution and flux. It's very challenging in nature to measure just the size distribution of a single process. It's always a mix of source contributions. So that's still an uncertainty. Chemical composition is challenging. And the question would be, of course, are there other impurities released in significant numbers by this process back into the atmosphere? Another uncertainty in the model is how many particles are produced per sublimating snow particle. The model suggests 5, but there's no measurement really behind that. It's just a fitting parameter currently. And finally, also like the link to clouds relies heavily on the vertical transport to link, in fact, the surface emission flux to cloud level and how it impacts. So there's still a lot to do. Yes, and I end here. Thank you.
Thank you very much, Marcus, for this nice presentation. So we will then move over to our next presentation, which is by Rémi Lapère. And Rémi has been a postdoc within CRiceS for about 2 years, and he's working on regional modeling of natural aerosols in the polar regions. And I should say that Rémi has 15 minutes to present. Marcus had a little bit longer because he took the introduction. And then after that, we will open up for a panel discussion and questions as well from the audience. So please, Rémi.
All right, I'm assuming you can see the screen and hear me. So thanks, Annika, for the introduction, and thanks a lot, Marcus, for the excellent presentation. I will keep us going with some more considerations on modeling of marine aerosols in the Arctic. When I started my postdoc at IGE 2 years ago, a bit more than that, the first question we had was, do climate models do a good job at representing sea salt aerosols in the Arctic? And if not, should they care about it? Should they do something about it? The underlying motivation is illustrated here. It's that in a warmer climate, there's less and less sea ice, meaning that there's more and more open ocean in the Arctic. And more open ocean means more resuspension of sea spray from the ocean into the atmosphere. So if we believe that sea spray is important for climate, as Marcus said, then we can believe that it's important to get it right in the climate models if we want to reproduce the climate accurately, not only now, but also in future projections. So the first question is, should those models care about the sea salt they put in the atmosphere? For that, we used these experiments from CEMIP6, which double emissions artificially. So they in this case, double the emissions of sea salt aerosols all over the world. And we can see the response in radiation related to a doubling of the sea salt emissions in one particular model, which is CRiceS. And we can see that there's a cooling effect of a few watts per meter squared in the central Arctic when you double sea salt aerosols. Okay, let's keep that in mind. At the same time, we can look at different models, how they represent sea salt emissions in the Arctic. This is a plot with each individual line being one CMIP6 model, and this is the average annual cycle of sea salt emissions in the Arctic. And you can see that they are essentially agreeing on the annual cycle, but they're all over the place in terms of the magnitude. There's a difference of a factor by up to 3 between the lowest emitting and the highest emitting model. So quite a big uncertainty on how much sea salt is actually introduced into the Arctic atmosphere, if you believe climate models. And at the same time, they tend to all overestimate concentrations of sea salt. This is just an example for a station that's located in northern Finland, with the observations in black and the models in blue. But you can see that they're overestimating sea salt by a factor of up to 3, but individual models can go as high as 10 times the concentration that's observed. So if you combine all those pieces of evidence, it's fair to say that there's quite a big uncertainty on sea salt aerosols at the poles in climate models that could introduce a bias of several watts per meter squared. And because there is a positive bias, so an overestimation of sea salt, maybe the cooling in the Arctic is a bit too strong in climate models compared to what it should be. But in the end, it's not big a deal. It's not that big a deal if it's a constant bias, meaning that if the seasonality is right all over the Arctic, but it's just a constant bias, it's quite easy to fix in a model. We can just shift by a factor, right? But if the seasonality is wrong, it means that processes are not captured as well as they should. So let's look at the seasonality compared to observations. Let's first start with a station that's in Iceland, so not really affected by sea ice. And let's look at observations there. So that's the black line, and the models, how they represent the same quantity. This is all bias corrected, right? To just see the seasonality and not account for the bias. And we do get a fairly good representation of the seasonality of sea salt aerosol at that location. If we go a bit more to the north, say at Utqiagvik in Alaska, we get also a fairly decent seasonality, but we do miss that wintertime peak in sea salt aerosol that's in the observations, but not in the model. And if we dare going even more to the north and closer to sea ice, like at Alert, which is surrounded by sea ice throughout the year, you get that the seasonality is completely off. And that is pointing us in the direction that these climate models, they don't include sea ice sources of sea salt aerosols. As Marcus said, they consider that there's sea ice, so there's no such thing as emissions of aerosols. And that's the reason why they get the wrong seasonality. So they do not get it, right? What can we do about it? Marcus talked about blowing snow quite a bit, and he showed that we can improve things if we include blowing snow. And I'm going to touch upon leads myself. So can we improve seasonality of sea salt aerosols in the Arctic in climate models by introducing leads, emissions from leads? So leads, they are these elongated cracks in the sea ice that expose open water to the atmosphere. And we don't really know how exactly it's going, but they release sea spray into the atmosphere. I'm not going to dive into what processes could be at play, but essentially when you open a crack in the sea ice, you get the release of sea spray. And then the sea spray can be transported further away and impact clouds, as Marcus touched upon, or maybe deposited onto snow and then resuspended through the blowing snow mechanism. Right. And at the moment, this is how leads, specifically leads are represented in models. They're not. There's no such thing as sea spray emissions from leads in models that I know of. So we went ahead and tried to build a parameterization ourselves to get an idea of how much could be emitted from leads. And to build the parameterization, there's essentially two questions we need to answer. The first one is how much is emitted by a lead? And the second one, where are those leads? And if we can answer these two questions, then we have ourselves a parameterization of emissions from leads. For the how much, we use data from the Arctic Ocean 96 expedition, where they measure total aerosol flux over open ocean and over leads in the Arctic. And this is super interesting data, but for modeling purposes, the problem is that we need that flux for each different size of aerosols. This is just an aggregated flux for all sizes that's only dependent on wind. But we can be clever about it and come up with some kind of ratio that will be the relative contribution of leads versus open ocean for a given wind speed in emissions of sea spray, and then apply that ratio onto better known parameterizations called source functions of sea spray that we use usually over open ocean and that do have this size difference in the flux that is emitted. So essentially, we apply some kind of ratio onto usual source functions of sea spray. So that's for the how much. For the where, our first instinct was to look at satellite products such as this one by Wilmes et al. In 2023, where essentially they look at thermal contrast in MODIS, and they say where it's warmer, there's a lead, essentially. And that's super high resolution, super interesting product. But the problem is it's limited for what we want to do because there's data only from November to April, first thing. And second thing, these products detect also leads that are covered with thin ice. So technically they are still leads, but they're not interesting for us because they cannot emit aerosols, at least sea spray aerosol. So that's a no-go for the satellite product. So instead, we turn to modeling-based product with this NEMO-NextSim sea ice model that's developed by colleagues at IGE. And we extract the open water fraction in the pack ice from this high-resolution modeling. So that's for the where. So it's a good thing we answered both questions, how much and where. So now we can implement that into a model. But first, before going into super complicated models, such as WRF-Chem, which is a regional atmospheric chemistry model, we first implement all these formulas into a toy model or conceptual model to kind of look at what are the orders of magnitudes we are dealing with here. And when we do that, this is sort of what we get. So there's a lot going on here. Everything that's purple-ish has to do with leads. Everything that's blue-ish has to do with blowing snow, a similar formula that Marcus showed, but somewhat more simplistic, let's say. And everything that's black has to do with transport of sea salt. So all of the sea salt that's coming from the open ocean and that gets transported into the Arctic. So these computations are based on reanalysis data. And you can see from this animation and from the time series that in the winter time, transport is the dominating source of sea salt entering the Arctic. And second comes blowing snow, and third comes leads in terms of mass. All of the solid lines are mass, and the dashed lines are number, right? But as the year progresses, and we reach the summer month, leads become progressively more and more important for the budget of sea salt aerosol in the Arctic, so much so that it goes above transport. So in the summer month, leads is even more important than transported sea salt aerosol mass from the open ocean. However, if you look at number concentration and not mass concentration this time, I mean number emissions, so that's dashed lines here, blowing snow is always more important than leads, except maybe in summertime when leads can reach a similar amount of number emitted particles. And that difference between mass and number is important to consider in modeling because depending on what kind of microphysics, i.e. aerosol cloud interactions you represent, number or mass can play an important role in how you represent clouds. So what I'm trying to say is, if you had a model with blowing snow and leads, be careful of what microphysics scheme you're using to draw conclusions on the importance of each of these sources. All right, so that's a good first idea of the orders of magnitudes we are dealing with. But if you recall, the motivation initially to build this parameterization is because in this plot, we had that the CMIP6 seasonality was wrong at high latitude near sea ice. So did we fix anything by including these sea ice sources? So let's have a look. It's still an idealized framework, right? But let's have a look. So in both plots, the dashed black line is on top is actual CMIP, and on the bottom is the idealized CMIP6-like annual cycle of sea salt concentration in the atmosphere at this alert station that's close to sea ice. And in gray are the observations. And the blue and brown are if you consider only emissions from blowing snow and leads near alert. And you can see that it's not perfect, but all of a sudden you get a much better agreement on the seasonality of sea salt aerosol concentration if you consider even only CI sources of sea salt aerosols, that would be leads and blowing snow. So even in this idealized kind of framework with a quite, say, basic parameterization of leads, we get the sense that indeed we could improve the seasonality in climate models by including CI sources of aerosols, which kind of proves our point that this is what was missing to begin with. Oops, sorry. So in conclusion to this part, sea spray emissions from leads do matter for Arctic aerosols. But to get a better look at the climate impacts on clouds especially, I think us modelers would need some more measurements, especially size distributed, size resolved fluxes of emissions from leads, not only of sea salt, but also of organics, which can have an influence on the cloud phase and so change the influence on the radiative budget. For those interested, there's a paper out on just that. So this parameterization of sea spray from leads and its implementation, both in the toy model and in the WRF-Chem code. I didn't touch upon the WRF-Chem version of it, but if you're interested, go look at the code and at the manuscript. Okay, so far we've touched upon only primary aerosols, right? So aerosols that are emitted into the atmosphere already in their aerosols forms. But as Marcus said, there are also some aerosols that are secondary. So they are formed from the condensation of gases, such as DMS that's found in the ocean. So I'd like to finish this presentation with a word on how DMS in the ocean, so essentially biological life in the ocean, can affect Arctic aerosols. So DMS is emitted in the atmosphere via biological activity in the ocean. And then when it's in the air, it gets condensed and form, for example, sulfate aerosols, which are very efficient at seeding clouds. So really relevant from a climatic perspective. And we started working on how we can best represent this in our WRF-Chem model. So again, this is a 3D regional atmospheric chemistry model that we use for Arctic applications. And this is how, like the situation, say, a year ago, before we started working on that. This is how DMS was represented in WRF-Chem. Just a set of 3 DMS reactions, so how the gas transforms into aerosols. And quite, let's say, general climatology of oceanic DMS. This is quite a famous product for modelers, this Lana et al. Climatology. But we know that only these 3 reactions is an oversimplification, and we know that this Lana product is probably not really valid in the Arctic for lack of observations. So we went ahead and updated our models in these 2 fronts. So there was a development made by Louis last year, where we moved from 3 reactions to a set of 17 more complex reactions. And at the same time, through a collaboration with our colleagues from the University of Victoria, so Nadia Steiner and Antoine Adon, we replaced this climatology that gave us monthly values, not very Arctic specific, with detailed biogeochemistry simulations of the Arctic Ocean. And so we get a much more detailed view of how much DMS is in the ocean and a more detailed view of how it acts in the atmosphere. And when we put these 2 in the models and we compare with the previous version we had a year ago, here's the result on the number of aerosols in the atmosphere. So that's a 100-kilometer resolution simulation for a few months. And we get an increase even over sea ice regions of more than 80% in aerosol number, just by updating the chemistry and by substituting a coarse climatology of oceanic DMS with detailed simulations. So I'm not going to go much further on that. There's a lot ongoing at the moment, but the message is check your DMS, be it in the ocean or in the atmosphere. It will be important for your Arctic aerosol in your models. Right, so I will stop with a few concluding thoughts. Each of these sections led me to questions or thoughts. And the first section is like, do we need accurate aerosols in climate models? That's kind of the whole topic of this webinar. Because I said that sea salt aerosols are worth a few watts per meter squared in climate models. But don't they have bigger fish to fry to maybe represent the climate better? Like say clouds that can represent tens of watts per meter squared. So that's a question. Then the second section, so this whole leads parameterization, made me wonder, is something enough to start modeling? Like I know modelers have been afraid sort of including this lead parameterization in the past because they didn't have enough data. And well, I said to myself, I have something, let's just start and provide some first orders of magnitude, and then maybe motivation will will follow for other people to take on this work and improve. So I'm just saying, even if there's a little something, just I think it's enough to start modeling. And obviously, the last part shows that it's super important to have interdisciplinary collaboration in projects such as CRiceS, because if I hadn't talked with Antoine and Nadia, I would never have tried their product for the oceanic DMS that has a big impact on aerosols in my modeling experiments. And finally, I would like to acknowledge the funding from CRiceS and thank all the collaborators that have contributed to this work. Thank you.
Thank you, Remy. I think you can keep your last slide up there, actually, because we could return to those questions, I think, during the panel discussion. So I will now invite the two other panelists in addition to Marcus and Remy. So we have Ruth Price also from the British Antarctic Service, and then we have Ulas Im also from Aarhus University. So just to give you two a chance to introduce yourself, so maybe we can start with Ruth. If you could just say a few words about yourself, and then from these two talks now, are you convinced? Do aerosols from sea ice sources, does the climate care?
Thank you, Annika. Thank you for the invitation to join this. I am a postdoc at BAS. I originally did my PhD at the University of Leeds, where I was working on polar aerosols in UKCA, which is used in the UK Earth System model. And now I work on the PolarRes project, which is kind of a sister project to CRiceS, and that's kind of how I became involved in these discussions. I think I'm pretty convinced that we have at least very good reason to believe that the climate would care about these sea ice sources. I think the talks have shown that these sources can make a very significant difference on the Arctic aerosol budget, certainly. Maybe we haven't answered all the questions. I think there's a lot left to explore, but I'm pretty convinced.
Okay, good to hear. And then Ulas, what is your opinion? And could you just introduce yourself briefly?
Sure. Thanks, Annika, and thanks for inviting me to this discussions. Thanks for the two speakers. I think it was quite inspiring and very exciting. So my name is Ulas Im. I'm a senior scientist at Aarhus University, Department of Environmental Science, and I'm also a modeler, both regional and global scales. And my recent interest the past few years is on natural aerosols, especially over the Arctic, but also globally, which kind of tells you that I am already convinced that there should be a climate impact of these aerosols, especially in areas where the background concentrations are quite low. We already know, as a matter of fact, that even small perturbations to these concentrations can have large impacts. So, I mean, quite shortly, I can say yes. I am also quite, as Ruth said, convinced that there should be an impact. The impact, the magnitude of the impact and the extent of the impact is quite uncertain, as we heard from both speakers. But I think we should just keep introducing more knowledge into our models and understand these interactions.
Mm. So maybe also the two of you can briefly say something about, so you are both using global models, transport and climate models. So do you have any sea ice source in these models? And would you say that's typical?
Shall I go first?
Yep.
So
sure.
yeah, I use the kind of UK global aerosol modeling component of the Earth System model. That currently doesn't have blowing snow, although some of our colleagues at BAS with Marcus are working on trying to get that introduced and looking at the effects of that. In terms of open leads, I would say not really, because in the global model, there's no specific lead parameterization like what Remy has introduced. It just kind of considers a sea ice fraction, and it says, okay, the pack ice region might have like 80% sea ice, so let's emit aerosols as if it were open ocean for 20% of this model grid box. And that's really kind of not good enough, I think, as Remy has shown. So I think we're kind of in a good position where the work of like what Remy has been showing is setting things up quite well for Earth system models to be introducing these. I don't think, my impression is that there's not many Earth system models that have sources like these, but maybe that is rapidly changing now.
Yes, maybe Remy, you can just jump in there and say, would you say that the parameterization that you have developed for leads would be suitable also for a global model, because you use the regional model here?
Yeah, so definitely that was one of our purposes to begin with, was to create something that's not too complicated, that depends on really accessible variables that are in these global models. And also that's also one reason why we didn't go with that satellite lead detection thing, is that we didn't have, like, it was super high resolution, so that's no need for a climate model to go 1 kilometer resolution. And also there was no data in the summertime. So we wanted to build something that's as easy as possible to implement in a global model. So definitely, I think it would be super easy for a climate model to pick up this parameterization. But I think it also deserves some more testing before. Like, we did the best we could with what was available. That was one of my points in the concluding thoughts, is that it's something, but it's not really well tested just yet.
And Ulas, do you feel that you have enough for implementing this type of parameterization in your model? Do you have already some parameterization in the GIS model that you're using?
No, we don't. I think none of the Earth system models has these processes. But I really agree with how Remy concluded his presentation. I think we should start somewhere. We cannot just sit and wait enough data to be, collected from all over. And yes, there are challenges regarding the resolutions of these models. I mean, the model I use is more than 2-degree resolution. So having these small features, would they really mean anything? That's something to test, of course. But we have more and more this kilometer scale climate models entering the market now, right? So I think these are also tools that we can further test these parameterizations and see the magnitudes match, for example, compared to what Remy has come up with. So I think there is promising progress in that direction that we should acknowledge and start using.
So I'd like to ask Marcus a question now, but I would also like to tell people that please raise your hand if you have any questions, because I think we will have time to let also people ask some specific questions to the speaker, or maybe since we have the panel here, if you have some more philosophical questions. But Marcus, so when you hear now that the modelers are quite eager to start looking at both lead emissions and blowing snow, how can modelers help you in the work, like also when you work with observations, and maybe say something, what do you need from the modelers, the other modelers?
I must say, like, the collaboration with modelers is fundamental. I mean, the blowing snow research was hypothesis driven by a model hypothesis, which took us out to undertake an Antarctic winter expedition. So we knew that if there's a source, it's in winter, it's in the sea ice covered ocean. Let's go there. So like, we need kind of these kind of directions, where and when to go, but then also which parameters are actually the most important one. And then you can find out only through some sensitivity study which should be put most emphasis on given limited resources, like for these complicated instruments. So that's, I think it's quite vital that the modelers are there on board from the very beginning of a project.
And maybe also in the end can help you tell, like, which, a bit like Remy was asking there with one of the questions, we can't maybe implement everything. So what should we focus then later on as modelers to have the interaction with you, we focus on the observations. So Sharat, you have a question.
Yes, hi Marcus, hope you're doing good. So I have a small doubt. So it's like, how important the microbiology in the sea salt aerosols? Do you think sea salt can act as a transportation vehicle for the sea salt? I hope you
mean you mean like a sea salt aerosol as a vehicle for other contributions, for marine organics, for instance? Yes, I mean, for sure.
And
I mean,
how much
the model is like, of course, considering also like a pure sodium chloride particle in nature. This doesn't occur.
So don't you think the pure crystal of sodium chloride can affect the microbes? And do you think any studies has happened studying these interactions that you know?
Oh yeah, so feedback to ecosystem, etc. I'm not a biologist. I defer this to anyone in the audience
Okay.
who's
Yeah.
an expert in this. Yeah.
Okay, yeah, so lots of additional things that will be interesting to study here. So we have also Jurgita, if you want to ask your question.
Sure. So I'm Jurgita Obernawaite from University of Galway, Ireland. So I have maybe more philosophical question, and starting with Marcus, like you indicated the warming from the sea salt, so I understand from indirect effect, and Remy was referring to the cooling. So which one is more important, like, and how do you think like the warming works like through the clouds? Like why is it warming, not cooling via clouds? Yeah.
Sorry, I mean, maybe as I explained, I mean, the effect model was here, like, what's the impact on increased cloud condensation nuclei coming from a surface source on clouds? And the constraint was observed liquid water cloud path. So that it's being constant. As you increase the CCNs, you increase cloud droplet number, which makes the cloud more optically thick, and then therefore increased downwelling infrared. And that's the warming. But of course, there's other effects. There's like secondary indirect effects. And I think overall, these indirect effects are not very well represented in the models. Remy can maybe elucidate there.
Yeah, I agree, definitely. Yeah, sorry, Annika.
No, go ahead.
No, I just agree with Marcus that there's quite a lot of work to do on these aerosol cloud interaction representation in models to really be sure even of the sign maybe of the response. And yeah, and just want to comment on that our colleague at Latmos, Louis Marel, just published something super interesting on aerosol cloud interactions, where he shows that getting the background of aerosols right is even more important than having the parameterization of aerosol cloud interactions right, which I think is super interesting, and I highly recommend anyone interested in that to have a look at his paper.
Yes, I agree. And we should also thank Jurgita for being on the CRiceS advisory board, so bringing up these type of interesting questions that we can also continue working on. And I think the level of the liquid water path that is originally there in the models is super important then for saying if it's going to be a cooling or a warming effect, because that really tells you if it's sensitive to if the long wave radiation is sensitive to the increase in cloud droplet number concentration or not. So I'm just thinking also it would be nice, since you touched upon this a little bit, that if we think of the future, and if models now, this is going to be a difficult question, I think, but if we think of that models now do not have the right background concentrations, and we go into the future, do you have any feeling for, do we overestimate or underestimate what will happen like with the warming in a future climate because we are missing this source? Who wants to start?
Yeah, I mean, I can say
a
few things if I'm allowed to. Yeah, I think that's a quite interesting question and very important question, because it kind of tells us how we should respond or mitigate climate change, right, to a possible extent. And we already assume that we will have a cleaner atmosphere, anthropogenically speaking, in the future, with a relatively larger contribution from natural sources. And with the warming and, you know, all these leads and open ocean in the Arctic, for example, we will be emitting maybe much more of these natural aerosols. So I think it's quite important to take these into account already now, if we want to really make proper projections of what the future climate would look like. Yeah.
Yeah. Any other comments from the other panelists?
Can I comment on that as well? So I think you've made a really important point of a lot of the focus in these talks has been on like putting new processes into models, and I think the motivation for that is really clear, but you need to not forget the existing context of the models. And like Remy was showing in the earlier parts of his work, he showed that even without thinking about these polar specific processes, there's already a lot of uncertainty about, for example, polar sea salt. So I think there's like an interdisciplinary aspect here as well. You need not just, biogeochemists or sea ice modelers, you also need different types of modelers like Earth system modelers or statisticians who can dig into like, how are you affecting the existing uncertainty of your model. I also wanted to pick up on a question that was in the chat from Ross Herbert, because he asked about the future as well. And he was saying, do you think that these things will balance out when there's less ice? So there would be less flowing snow and fewer leads. Do these changes maybe balance out? And I don't think we can necessarily answer that yet, because there's a lot of uncertainty in, for example, the marginal ice zone. So that kind of region between open ocean and very consolidated pack ice where you have leads, that is kind of expected to almost expand. You'll have less multi-year ice, more first-year ice in the winter. And I don't think we have a good handle on how these open lead aerosol emission processes are affected by those changes. So I think that's kind of an open question. The other thing I'll just quickly say is, in terms of modeling the future, I think even if we get ourselves to a position where we have perfectly tuned CMIP style models that have these polar processes in them, I think we kind of need to ask ourselves, what then? Because the kind of global aerosol modeler perspective is that you look at the effect of aerosols in the system, especially natural aerosols, by doing the kinds of idealized experiments, which again Remy showed at the beginning, of like, okay, let's do 2 times sea salt and see what happens. But by definition, you run those experiments with a fixed climate state so that you're only isolating the aerosol effect. And for what we're talking about, where the changing aerosol sources from a change in the sea ice state, that kind of experiment almost misses some of the point there. And I don't think at the moment there's a great way of kind of digging into how will the combination of aerosol changes and sea ice changes, kind of what's the net effect of that on the global system.
Yes, this is definitely something that we can also work on more than within CRiceS and also in PolarEst, and maybe as our sister project. So I was also notified here that we had some questions in the chat, and I saw that one of them was actually very similar to what we discussed now, so that was good. But I'd also like to bring up here, because there's a question about the Southern Ocean, and we have focused mainly on the North Pole. So are there any differences that we need to think about when coming to the Southern Ocean?
I can just maybe quickly comment on that, because this evaluation of CMIP models that we did was not only for the Arctic, but also for the Antarctic. And essentially we had the same general comments about it, like overestimation of sea salt and some problems in the seasonality of sea salt aerosols. That's at least one thing.
Thank you. So we are almost running out of time here, but I would like to give you 30 seconds each to say what will be your next step for improving our knowledge on this topic. So let's start with Marcus.
Yeah, I'm following the inspiration of Remy. You need definitely an observation-based parameterization of open lead emissions, fluxes, etc., of sea salt and other species, including probably the MSA. And that's maybe a good input also, like for planning for the International Polar Year 32 or Antarctica InSync, of these big multinational interdisciplinary programs where these ideas feed into and which drive then our measurement strategy.
Great. And then Ulas, what do you say?
Yeah, well, I mean, what I will do, of course, I'm quite interested in implementing these parameterization in the models, but I would also advocate for, as Marcus already said, more measurements, because quite most of the time when we try to model new tracers or new parameters in models, we already start struggling from the beginning of the fluxes. We never know what the real fluxes are. We don't have any size distributions. We just assume that they are either constant. We have no idea what the order of magnitude of the fluxes are. So anything we model is already a question mark to begin with. So I think we should really do more to observe more than concentrations, but also look at the fluxes. So more flux measurements would be a good start. And for the modeling part, I think there is of course all these natural sources from sea ice, but there are also tons of other tracer species, VOCs, that we barely know, and we have no representations in the models. We don't even know if they really matter, which is the question of this webinar anyway. But I think there are lots of natural sources that has to be in these climate models somehow.
So this was your work for quite some time.
Oh yes, that's a long work, yes, and not only
Ruth?
my work,
sorry.
hopefully.
Yeah, Ruth, what will you go back and do now?
Yeah, I
On
think
this topic?
I think it's quite an exciting time with these new parameterizations coming out. That it will be kind of a new generation of models, hopefully, that have these polar specific sources that we haven't had before. So it's kind of like, if you're nerdy enough about this kind of thing, it's almost like having a new toy. Like it's quite an exciting time to see, once we start digging into, like, yeah, really what are the cloud effects of including a parameterization and aerosol source like this in the polar regions. I think there's a lot of work to do there, and some good data sets as well that already do exist, although of course more observations are always helpful.
Rémi?
Yeah, for me, I think that it's the fact that there's a lot of life under sea ice, which can affect how much biological stuff is emitted into the atmosphere, or organics. And with this lead parameterization now, I can sort of take into account the life under sea ice and how it affects the type of aerosols that's emitted, which in turn will affect cloud phase. So I think that's one of the topics I want to focus on.
Excellent. And biology will change with climate warming as well. So that's also interesting. So thank you to the panelists and speakers. This was really great. And before you all leave, I want to give the word to Paul Tiger, who's going to market a scientific collaboration network that some of you might be interested in joining. So Paul, please share your slide. And I would like to thank again the speakers and the panel.
Yeah, cool. Thanks a lot. And thanks a lot for this nice discussion and these nice presentations. It was really interesting and joyful to listen to. I'd just like to spend 2 minutes to make advertisement for one of those initiatives that are relevant for these topics, and it's called CATCH, the Cryosphere and Atmospheric Chemistry, that I'm co-chairing together with Jesse Gremian from Colorado State University. And CATCH's mission is actually to facilitate the interdisciplinary international research to understand the system that controls atmospheric chemistry, and it focuses on these specific processes that we just talked about. And we try to really develop develop this international transdisciplinary research community to foster research planning, to engage early career scientists, and also to engage with the public and stakeholders. And before my minute is over, I really like to encourage you to have a look at our website, catchscience.org, and also to sign up for our newsletter if you're interested in our ongoing activities. For example, upcoming conferences, the IPY planning workshop that also Marcus quickly mentioned, things like the Friday meetings, or also joint transdisciplinary conference sessions, for example, at EGU next year. So please sign up, and thanks.
Thank you, Paul. And don't forget also to go into the CRiceS website if you want to know more about what we're doing in the project. And then thanks to the audience for listening and asking good questions, and have a nice afternoon and evening. Bye-bye.
Thank you, Annika.
Bye.
Thank you all.
Thank you.
Bye.
Yeah, thank you,
Thanks
Annika, as
all.
well. Bye.